Welcome. I'm Miss Mike Sullen. I'm one of the material science engineering teachers at Eagle Crest High School. And this podcast is going to focus on processing metals, introduce you to the methods of heat treating metals to change their properties. So our essential question for today's podcast is, how does metal processing affect properties? And why is processing of metals important? The importance of metal processing has so many factors: economically, environmentally, politically, medically, industrially, mechanically, structurally, lots of reasons why if we change the properties of a metal, we can improve the function, the lifespan, the economic value, the importance, and make useful products in material science engineering. So, a touch of a review of old material as we lead into our new learning for today. To start with, let's think about crystal grains and boundaries. A grain is a tiny crystal that's part of a larger group of crystals. And the boundary is the interface between two grains or crystallites in a polycrystalline mini crystal material. So we can see right over here in this microscopic image that this is a grain, and this is the boundary between one crystal and another. So again, this would be another grain, and this would be a grain boundary separating the two different grains. If you remember, when a crystal forms, that seed crystal grows out in all directions, and it will grow uninhibited until it meets the boundary of another crystal, and that will interfere with its growth and stop it from continuing. And so since that's happening simultaneously all over, you get this polycrystalline material, or multiple grains forming with lots of boundaries in a polycrystalline material. So we can see that our structural changes occur with temperature, because as atoms are melted, that melted metal is going to begin to pack together to form the crystal lattice. We're going to start to have those seed crystals and the early groups of atoms forming tiny crystals, which is going to result in grains. And those grains are going to grow until they reach other crystals and they are forced to stop. And that's what creates the grain boundaries and our polycrystalline material. So the key to today is that the faster the material is cooled, the smaller the crystal grains are. So if we're looking to control grain size, we want to cool the material quickly. So we're going to explore 3 different heat treatments today. We're going to look at how metal can be annealed, quenched, or quench tempered. And these 3 different heat treatments will affect not only the grain size of the metal, but also the number of defects and dislocations and the metal's properties. As we start to explore this new material, we need to cover a couple of new vocabulary words. The critical point is the temperature of a metal where recrystallization occurs. In other words, this is where the metal becomes liquid and melts enough to where you'll get new crystal formation and growth. If you heat a metal above the critical point, new grains or crystals form. So remember, if we're changing the grain size, we can change the properties and function of a metal, and we're going to do that by recrystallization. In science, a control is an untreated material used to minimize the impact of other variables and increase reliability. It's used as the baseline to making comparisons. Dry mix is a helpful acronym to think about a controlled experiments. The independent variable is manipulated and always is placed on the x-axis, whereas the dependent variable is the responding variable and goes on the y-axis, and the controlled variable is the unchanged variable that you use to make comparisons against. So when it comes to grains, size matters. Large grain metals are very soft and easily workable, but they're not as strong. If you remember back to the What is a Metal lab, you'll remember that lead was extremely easy to manipulate and work in your hands. almost didn't feel like a metal. It was so soft, right? And that's because it had very large grains. Whereas small grained metals are very strong, but they can also be extremely brittle and not very workable. An example of that would be steel. So there's always a trade off for material science engineers between strength and workability. So let's get into the three different types of heat treatments. Annealing is the first type of heat treatment we're going to look at. Annealing occurs when we heat a metal above the critical point, thus allowing for recrystallization, and then we allow it to cool very slowly. This increases the grain size, creating large grains, and thus this increases the workability of the metal but decreases its strength. Here's what the annealing process looks like for a metal. In this example, we're going to take a paper clip and we're going to heat it up to the critical point. Critical point meaning it's going to become red hot. That allows that recrystallization to occur. And then we're going to let it slowly cool either on a heat resistant tile or buried in sand if we want it to cool even more slowly, or in an oven if we turn the oven off and we want it to just cool in a very slow and extremely gradual manner. And the rate at which we have it cool will determine the size of the grains, how large we can make those grains. So we can see that if we want to anneal something, we're going to heat it right up to its critical point. Hopefully you're recognizing this is a binary phase diagram. And if we heat it above its critical point, how slowly we cool it will determine how large the grain size of the metal is. We want large grains to form with the slow cooling process to increase the workability of the metal, but not its strength. So let's look at an atomic view model. We've already examined this last semester, our BB case activity, where we can see at the molecular level what's happening when we anneal or gradually cool a metal over time. So you can see at the atomic level that you have extremely few defects. You have large grains that formed, very regular regions of that crystal structure, so very large grains. In fact, if I look at this picture, I really only see a couple of grains in it. We have extremely large grains that formed and very few defects. That's why annealed metals, because of their large grains and very little defects, are very soft, they're very workable, they are not strong at all. So the second heat treatment we're going to explore is quenching. And quenching heats a metal above the critical point and then cools it very quickly. An example of that would be quenching it in an ice bath. This decreases the grain size, creating very small grains, which in turn changes the properties and makes the metal much harder, much stronger, but also much more brittle. If we look at the process for quenching, again, we're going to heat the metal to red hot above the critical point so recrystallization can occur. But then we're going to quickly place that metal into water to cool, thus stopping the grains from continuing to form and creating very small grains with lots of defects because we rapidly cooled it. Again, at the atomic level, we can see an example of what's happening with our BB case activity. So we can see much smaller grains in this model because we have a lot more defects in grain boundaries, and places where the regular crystal structure was interrupted by that rapid cooling. And this is what's creating our change in properties. So when we abruptly cool a metal, we get much smaller grains, and we also have more defects occurring. And the final heat treatment we're going to look at is something called quench tempering. It's also sometimes just called tempering. This is when you heat a metal above the critical point, cool it very quickly, i.e., quench it, but then you reheat the metal below the critical point to allow the material to cool slowly. The quenching forms very small and strong grains, but the reheating, the tempering, adds some workability. This is a compromise in terms of properties. You create a very strongish metal, not as strong as obviously quenching by itself, but pretty strong. But it's also not as brittle. You increase some of the workability through the tempering process. So this is as good as it gets in terms of wanting to get a strong metal that is also workable. Again, this is what that process would look like. You're going to heat the metal to the critical point, i.e., red hot, to allow for recrystallization. You're going to quench it by quickly placing it in the water to cool. And then you're going to reheat it over low heat. Instead of a Bunsen burner, you might use a candle until a blue oxide coating forms. That reheating over low heat is giving the metal thermal energy to reposition the atoms within the crystal structure. In other words, it's decreasing your defects. And so when it decreases your defects, you're restoring some of the workability into the metal, because dislocations cannot easily cross grain boundaries. Atoms get tangled and pinned at dislocations, which strengthens the metal. So when we do the tempering and we allow a solid state phase change, some of those atoms to move in the crystal lattice with that low heat energy that's being provided, we are increasing the workability of the metal. Again, if we look at a binary phase diagram for steel, when we temper, we're going to be down here below the critical point. We are not allowing recrystallization, but that increased thermal energy that's going into the metal will allow the atoms to reposition themselves. It's going to decrease the internal stress in the metal from defects, which increases its workability. So, where we're headed. As we heat treat metals, we're going to be testing their mechanical properties. We're going to be looking at how those metals deform when stress and strain is applied. When stress is applied. So elastic deformation is when a small amount of stress is applied and the metal is deformed, but when the stress is removed, the metal returns back to its original shape. An example of something that can be elastically deformed would be rubber bands. You can stretch a rubber band, but then when you let go, it returns back to its original shape. Plastic deformation is when you apply a larger force and the material changes shape, and that force removes the materials and changes its shape permanently, right? So once the force is removed, the material will not go back to its original shape. It is now a permanent change in shape. An example of plastic deformation would be saran wrap. If you stretch saran wrap, you're never going to get it back to its original position. Which leads to where we're going as we start to look at how metals can fail over time and the fractures that occur when stress is placed on them. We can see A is an example of a brittle fracture, meaning there was no plastic deformation. When stress was applied to this cylinder, this metal cylinder, it broke. It was very brittle in terms of its properties, and stress was applied and it broke almost instantaneously. Whereas B and C show a metal that is more ductile, more workable, and as stress is applied, we can see metal C has some extensive necking. It experiences a lot of plastic deformation. It's not going to return to its original shape before eventually it fractures. Whereas B is moderately ductile, it had some necking, some plastic deformation before it fractured. So if you look at this fracture, this failure type, can you deduce the metal's properties? Is this a metal that was highly workable, ductile, or is this a metal that was brittle but very strong? Hopefully you told me this was pretty brittle and very strong because I don't see any indication of necking. This seemed to fracture pretty instantaneously. Whereas this metal definitely was more workable and more ductile, not as strong as the first one, but we can see examples of more extensive necking before it eventually failed. I hope this podcast was helpful. Enjoy the heat treatment of metals lab that we'll be doing next class.